Okay, we are off to chapter 20 here, second to last one of the season. We're going to talk about transition metals and coordination compounds. So we're going to first talk a little bit about transition metals, then the bulk of the rest of the chapter will be on coordination compounds, complex ions, and all that fun stuff. So we're talking a little bit about some trends and stuff that we see, and sort of related to transition metals. That's because a majority of complex ions in the center of them are transition metals. So one thing that you might have learned before was what is referred to as effective nuclear charge. Effective nuclear charge is sometimes referred to as Z effective. And it is sort of the positive charge that's felt on the electrons coming out from the nucleus, depending on really their distance from the nucleus. So if we take our good friend lithium there, which is 3. Electron configuration 1s2, 2s1. So when we have something like lithium, it has a positive 3 charge there in the nucleus, again from its 3 protons that are hanging out there. It has these sort of core electrons, right, which are the lower energy electrons, which are near the nucleus. Then it also has these higher energy electrons, which, as you should be familiar with, are the valence electrons, right? Our valence electrons are the outermost electrons. They are the important electrons because they really are the ones that are involved in bonding. So we got like another one, this guy's on the n equals 1 energy level, n equals 2, got the electron out there. So there is sort of a difference between sort of the positive charge that the core electrons feel versus the positive charge that those valence electrons feel. And that really is what Z effective is. So if we look at these sort of core electrons here, pretty much they are right there in front of that positive 3 charge, if you will. So they are feeling the full brunt of that positive 3 charge, which obviously is going to bring them in closer. Remember that electrostatic attraction, positive, negative attraction, sort of the strength of it increases with the increased number of charge. So that's really going to keep those guys tight. When we look at something like our valence electron, which is hanging out there on the outside here, this guy right there, he's not really feeling the full force of that positive 3 charge because he's experiencing what we like to call shielding. And basically, that electron on the outside there is shielded from the full positive charge of that nucleus by those lower energy electrons. They kind of get in the way. So instead of maybe feeling the full brunt of that positive 3 charge, it's now feeling a little less than that. And you can calculate the Z effective by taking the number of protons minus the number of core electrons. So in this case, we would have like a positive 3 there for our protons, and then we obviously have 2 electrons in the shielding sort of thing. So that outside electron is actually only feeling a positive 1 attraction to the nucleus. And that is why when we talk about sort of bonding and things of that nature, it is those valence electrons that are used in that. They are the outermost electrons, highest in energy, and frankly, they're not held as tightly as those core electrons. So they are the ones that are involved in bonding. Any questions on that there? So when you look at Z effective, it is related to the radius. We see that an increase in the Z effective, that's sodium, magnesium, aluminum, and silicon, that is period 3 on the periodic table, going across the periodic table as you go down. And as we go to the right on the periodic table, we do see an increase in effective nuclear charge. That's because as you go to the right on the periodic table, there's more protons over there in that region. The result of that is a greater positive charge, which is going to bring all the electrons in, and that's what we see in terms of our radius. In terms of size, right? Size starts to decrease as you head to the right and up on the periodic table because of that. And that's what we see here. Again, up to the right, size gets smaller, effective nuclear charge gets larger. And again, kind of the greater feeling of that positive charge to the nucleus. Even those outside electrons, just as a whole, going to bring everybody in, going to create a smaller overall size. Obviously, it increases as you go down size and decreases Z effective as you go down. The transition metals are found obviously between group number 2 and group number 3 on the periodic table. Those are our transition metals. We know transition metals probably for the most part because they can have a variety of charges, right? So when we name these guys, these are the guys we typically use Roman numerals to indicate the positive charge that's on it, except for a couple, which is right, our few, which is right here. Although these guys right here are transition metals, they have fixed charges, where zinc and cadmium are +2 and silver is +1 when it forms a charge. Other than that, pretty much most everybody else on the periodic table there are in the transition metal region. And even to the right of the transition metal region can make a variety of charges. Our transition metals do start at the D block, right? This is the S block, the first 2 groups on the periodic table. This is your P block coming this way in terms of electron configuration. And this is your F block on the bottom. These 2 guys on the bottom really go, if you count the atomic number right about there, really where those guys go. They're also sometimes referred to as intertransition metals because of that, because they technically should kind of go there into that spot. These are where a lot of our radioactive guys are, obviously over 84 in terms of the atomic number, as we talked about in the last chapter. You could also count electron configuration right off of the periodic table based on period number, but you do want to be careful because this, although it is in the 4th period, is actually 3D. When we talk about transition metals and electron configuration, underneath it would be 4D, 5D, and 6D coming underneath it in terms of electron configuration. So transition metals do show very similar, or very, I'll spit that out. I think they show great similarities within a given period and also a group. So like a lot of things on the periodic table, you know, if they're in the same sort of area of the periodic table, they do share very similar sort of properties. When they do form ionic compounds, more than one oxidation state is possible. And something like Mn, for example, can have a ton of different oxidation states all the way up to +7 down to +2. It can run like 7, maybe different oxidation states or so. Cations are often part of complex ions, which are species where transition metals are surrounded by ligands. We're going to talk a lot about sort of complex ions in this chapter, but basically a complex ion typically will have a positively charged metal in the middle. A lot of times a transition metal +2, +3 type of charge. And it will be attached to a lot of ligands, several ligands depending. And ligands are Lewis bases, and you're going to tell me Lewis bases are things that do what? Donate a pair of electrons, yeah. So Lewis bases are the guys that will donate a pair of electrons. And that makes sense because really in this case, the metal is acting as a Lewis acid. It is basically something that is electron deficient. It's electron deficient because it has a positive charge. So it obviously has given away electrons, which is why it is deficient. Here's a prettier picture, I guess. So here's our transition metal, or cobalt in this case, surrounded by 6 different ligands. NH3 is a really good ligand. A lot of good ligands or Lewis bases are things that are polar and have a pair of non-bonding electrons, like our nitrogen there on NH3. That is where it will bond into it. By the time we are done, you will know how to properly name this guy right here instead of that thing, the CO NH3 6. You'll be able to say that's like hexamine cobalt 3 ion, and you know, be happy about that, I suppose, or not. So most compounds are colored depending on the transition metal that's there, depending on the charge, and actually the ligands that are present will give that solution some different colors. You could have kind of the same metal in the center, but in certain cases, depending on the ligands and even the charge, in one case it may be like pink in color, in other cases it may be more of a blue solution. So it does give you different sort of properties, and you'll see different colors because the complex is able to absorb light of different wavelengths. And we absorb light, right? And the light that's being absorbed in terms of the wavelength is complementary to the color that we see, right? So that's why when we set something like a spec 20 or something like that to do absorbance, we set it to the complementary color of what the solution looks like, the wavelength in there, then that would be the right one. Many compounds are paramagnetic. Paramagnetic means some unpaired electrons happening there, right? Diamagnetic means they kind of pair off and stuff like that. So let's just remind ourselves about a little bit about electron configuration, right? Electron configuration for transition metals obviously does get us into the D range there, and electrons are obviously in different orbitals. Our subshells that are made up of orbitals. So S's, you can hold a maximum of 2, right? P's, if you filled up all the subshells, their orbitals in the subshell would be 6. D's, there are 5 different ones, which means you get 10. F, there are 7 different orbitals in a subshell, so you get 14 electrons. Remember, any individual orbital can only hold a maximum of 2. The order of electron configuration, as you may know, S's start on the first energy level, right? P's start on the second, D's start on the third, and F start on the fourth. If you remember that, then you can just fill this in and get the correct electron configuration order here. If you write the right letters next to it would be good as well. Let's try that. 4S, 4P. 4D, and then you can just finish it out there, just coming down. And you basically zigzag, right? Start at the top there, and then just keep going back and forth through each of these things. And that would give you the proper electron configuration. The major difference occurs right there with our transition metals. The S's are actually lower in energy than the D's. So they do fill up the S's first and then start filling up the D orbitals. So if we look at something like V there, which is 23, argon, which is noble gas configuration, that is the electron configuration for argon, continuing on 4s2 and 3d3. There are some exceptions that you might be familiar with. 2 very common ones most people are taught are chromium and copper. They are the exceptions to the normal electron configuration. Chromium, which is 24, if you follow the sort of the zigzag thing, you would end up with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d4. The exception for chromium and also copper is it's just been found more experimentally that there's an extra electron up there in the S. And by the way, again, this part right here, which is 18, is argon's configuration. And that's how we get to 4s1, 3d5. Basically puts an unpaired electron into each of the 5 different d orbitals, all parallel spin, which is pretty stable. Copper is the exact same exception. It's got 1 extra electron there in the D and 1 less electron there in the S. And again, they can do that because these guys are super close in energy to begin with. As you also may be familiar with, if you look on the periodic table below chromium and copper, and then kind of come down and then to the left a little and in, there's a lot of these sort of exceptions, like silver is an exception. PD has no electrons in the S. They've all been promoted up to the D. So there's a lot of these very similar sort of exceptions to electron configuration in that region of the periodic table. You may also remember that when these transition metals do go to lose electrons, they actually do lose the S's first, and that is because, as I drew there, although when they are going into the atom, the electrons go into the S and then into the D, what ends up happening is once the D's get populated, there's actually a switch in energy that occurs, and the 4s ends up being higher in energy than the 3D, which means that when they go to lose electrons, we always lose sort of our highest energy ones. We will lose those S's first. If you need more than 2 electrons, then you would dig down into the D's at that point to do that. So when you write electron configuration, you should have the S's come first and then the D's, because that is basically electron configuration, what is sometimes referred to as filling order. Sometimes you will see people write electron configuration where all the numbers go in order, like all the 4s, all the 3s, and all that are together. And that's usually written based on energy, which most chemistry classes don't do. So most do filling order, which is obviously the S's before the D's. All the transition metals pretty much do the same thing. When they lose electrons, they always dish the S's first, which comes before them, and then they go into there if necessary. So here we have Ti, which then becomes Ti3 plus. It obviously loses 3 electrons. Once again, it's going to take out the 2 from the S, and then we'll take out one of those guys there from the D, and that would leave it with this configuration right there. Question on that? So why don't you try one? Let's do iron. Let's do iron 3. Let's do nickel 4 plus. Iron is obviously 26 on the periodic table, and nickel is not 26, 28. All right, write the correct electron configuration for each of those guys. See what you come up with. Okay, let's take a look. So iron with the +3 means, obviously the plus means it lost electrons. 3 means it lost 3 electrons. So this guy is going with a 23 electrons. So that's going to be like a 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d6. This would be iron with no charge, obviously, in this case. I know I should have said that first. I know. There you go. Up to here, obviously, if you want to shorthand it, that would be argon 4s2, 3d6. So obviously, our iron with the +3 will take out the 2 there and take out 1 there. And that would then leave us basically argon 3d5 in this particular case. Any questions on that one there? All right, so nickel, again, with no charge would be argon, a little 4s2 action, 3d8. Obviously, nickel here with a +4 charge gets us to 24 electrons. So once again, we're going to take the 2 from the S first, because really they are higher in energy. We will then poach the next 2 from there, and that should yield us an argon 3d6 in this case. Any questions on electron configuration there? Hopefully I'll give it yeah. No, I don't mean to interrupt you, but no, if you're asking if somebody in the second row would lose electrons, they would lose their S's, but it would actually be their 5s electrons that would be lost on that one. So if we load back to, which I think was your question, I hope, where's that periodic table? There it is. So this is basically the 3D right here, and that's the 4s. So that row takes out those guys first. This is 4D, this is 5s. They would take those guys out first and so forth, and continue on the same way. Obviously, you would take out the 5s and then dig into the 4D. In that case, it was the second row. Yeah. Yeah. Mhm. No, hydrogen only has one S1, only takes one. What you might be thinking of is when you do bonding, for example, yeah. Hydrogen just needs to get to 2 electrons. And the reason for that is if you look on the periodic table, the next element past hydrogen is helium, which is a noble gas. And that's the point of all bonding, is to get to noble gas configuration. So for something like hydrogen, it just needs to pick up that one extra electron in a bonding situation to end up with this same electron configuration as helium, and it's happy. That's why everybody past basically helium there needs to get to 8, because that will take everybody to like neon, argon, and all those guys, which have 8 valence electrons, to be sort of stable in a bonding situation. Yes, sir. Yeah. Yeah. So are you asking about this one here? Or yeah. It did in this case because I'm just going to draw the last part there, right? So here's the 4s, right? And here's the 3D. This would be for iron with no charge, okay? So at the end, it looks something like this, basically. So that's like all the electrons there at the very end here. So that represents these guys right here. Yeah. So when this iron loses electrons, because there's really a switch that occurs, these 4s actually end up being higher. And the 3D end up being actually lower in energy. So we always kind of lose the highest energy electrons first. So in this case, because it made a +3 charge, it needs to lose 3 electrons. So the very 2 that will be lost first will be these guys, which takes out of our electron configuration the 4s, right? Completely. And then we still need one more, which actually would be this guy right here. Take out that guy, which would take that guy out. And that leaves us 1, 2, 3, 4, and 5 electrons still in the D subcell. And that's where the 3D5 comes from, yeah. And we've totally now just taken out 3 electrons to get us to that +3 charge. Other questions? So we talked a little bit about the oxidation states of transition metals. And like I said, there are a lot of different oxidation states that can happen. And it's sort of as you go through the first row there, peaks out there in the middle by Mn, which, as I said, has a ton of different oxidation states. For the most part, though, most commonly are the ones in red here. And for the most part, +2, +3s are pretty predominant, what you see in the transition metal regions, occasionally some +4s, but +2, +3s are very, very common in terms of the oxidation numbers. Another sort of trend with transition metals, just in general, is ionization energy. And as it says, that is the energy that's required to remove an electron from the gas state. When we talk about ionization energy and we remove an electron, somebody becomes positive. So this is usually associated with referred to as cation formation, right? Because that's what happens when you lose an electron, you become positively charged. By the way, electrons come off one at a time, so they don't all drop off at once. The general trend in ionization energy is it generally increases as you go up and right on the periodic table, and decreases as you go left and down on the periodic table. So, for example, if we take our good friend magnesium, and it decides I want to ditch an electron, the first thing that's going to happen is it will give away an electron and become +1 charge. And this is what is referred to as the first ionization energy. And that's the energy required basically to pull off the first electron. The next thing that would happen is actually that guy that lost the first electron would then lose another electron. And that would be what is known as the second ionization energy, the energy required to remove the second electron. And then, this guy here would ditch perhaps another electron and become positively 3 charged. That would be the third ionization energy, and so forth, if you continue sort of down that pattern. Is it easier to take away the first electron or the second one? Which one's easier? The first one's much easier. The thing's neutral, right? When you lose an electron, the overall size, does it get bigger or smaller, the ion? It gets smaller, right? Everybody shrinks down. Your electron field sort of got smaller, which brings those outer electrons now closer to the nucleus and that positive charge, which means they're going to be held tighter. And that's what we see when we look at this. If you look at this chart between the first ionization energy to the second to the third, the amount of energy increases as you do that. So for magnesium, it's 735 kilojoules there to pull off the first one. It doubles to about 1,400 or so kilojoules to pull off the second one. Then it goes about 7 times or so there, 6 or 7 times more energy to try to pull off the next electron, which frankly does not happen at that point. And that is because when you look at the electron configuration for magnesium, 1s2, 2s2, 2p6, and 3s2, magnesium has 2 valence electrons, right? When you get to that third electron, you are now in the core electrons, which are super close to electrons to the nucleus to begin with, and now find themselves even closer by the loss of those electrons, right? As everything squeezes in tighter, and it just doesn't happen in that case. That is why we don't usually see this, and we assume magnesium will head out there to a +2 charge because of that. We see the same thing here with sodium. Lose that first electron, 495. Lose the second one, you need like 10 times that amount. And again, because sodium has 1 valence electron, by trying to remove the second one, you're into those core electrons. It really just doesn't happen under normal conditions. So that's why certain things will make certain types of charges because of that. And obviously, as you can see, the general trend is from first to second to third, the ionization energy increases a lot. Any questions on that there? Here's a table of all the information you need to know. I'm just kidding. But our electron configuration we talked about size sort of decreasing as you go across. By the way, this is the first period transition metals heading in that direction on the periodic table. Our first, second, and third ionization energy. We also see overall melting point sort of decreases as you go to the right, and density increases a little bit as you go to the right as well. Here's our chart of our 2 things we just talked about. Blue dots is the third ionization energy, much higher than the first ionization energy. So that is the removal of the first electron versus the third electron. So again, it takes a lot more energy to do that. In case you missed the second guy, it's right there in the middle in the green. Let's talk a little bit about electron affinity. Electron affinity is the energy change that occurs when somebody gains an electron. When somebody gains an electron, they become an anion and negatively charged. And in general, electron affinity increases as you go up and to the right on the periodic table, decreases as you go down. It's not perfect, so this is like group 7 on the periodic table. And we do see it increase as we go up, but then it kind of comes down a little bit there with fluorine. So it's not a perfect trend, but that's the general trend that you do see. Just a reminder that electron affinity is the energy change when somebody gains an electron, and it is different than electronegativity. Electronegativity is the ability of an atom to bring electrons towards itself. Also increases up and to the right on the periodic table, decreases as you go down. Most electronegative element is fluorine, right? It's the most electronegative element you can have. So they are 2 different things. Sometimes people think they're sort of the same thing. So one is just the ability to bring electrons to yourself, and one describes actually the energy that occurs or change that occurs when you actually do gain the electron, probably as a result of bringing it to yourself in that particular case. Any questions on that there? Yeah. Yeah, it's sort of both of those things. It's very small, right? It's so small. That means getting any electrons to get near it will feel some of that positive charge from the nucleus. Also has obviously more protons than somebody to the left in a lot of cases. It has a lot to do with that in terms of that and its ability basically just to be able to kind of do that. And it is sort of, with all periodic trends, basically the most reactive non-metal is upper right of the periodic table. So upper right of the periodic table is fluorine. Going further to the right would be the noble gases, which are chemically inert, they're not reactive. So all those trends that we probably talked about in the previous class all lead to most reactivity of non-metals upper right. Most reactive metal would be lower left of the periodic table. And it has a lot to do with the overall idea of everybody's compact up there. It's going to bring everything closer into each other when they get near each other. Other questions? All right, in our table, like we looked at, this is the relative reducing abilities of the first row transition metals. And we see that reducing ability increases as you go up, which means that this guy up here on the top would have the highest reducing ability. These are all, though, written not as SRPs. These are all oxidation reactions. They're not like our SRP table. Our electrons are on our product side here. If we flipped all these reactions around, basically what would happen is a SRP table. And basically that would be negative all the way down. The guy at the bottom would become positive. So this guy would most likely be our cathode, right? And on this side up here would be our anode, or the guy gets oxidized. And if it's able to get oxidized, it's going to be a better reducing agent, right? So that's sort of how we looked at it before when we look up there. All right. This is what they all look like in case you need to pick them out in a lineup. All right, these are all the different oxidation states, which you guys really don't even do any qualitative analysis all that much anymore, so you don't have to worry about any of that stuff. There we go. All right, any questions on transition metals? So some of that should hopefully be a reminder, and you should be familiar with it, obviously. Where we're going to see transition metals here is in what we're going to talk about now, which is really complex ions and coordination compounds. So let's talk about what these guys are. First off, a coordination compound is basically like an ionic compound. So there's a positive guy and a negative guy. And like most ionic compounds, it pretty much kind of works the same way. We always go positive guy first, followed by negative guy, both in the formula and in the name. We also typically try to get ourselves to 0 when we have a coordination compound. And to do that, we have a complex ion and we also have a counter ion. So we have two things that make it up, a counter ion and a complex ion. And in certain cases, the counter ion could be positive and the complex ion could be negative, and vice versa. We could have a positive complex ion, and that would mean that we would have a negative counter ion to balance it out. Now, complex ion, as we talked about, is basically our metal, like a transition metal there in the middle, with our different ligands that are attached. So we talked about NH3 a second ago. We also got our good friend chloride here, which is Cl minus. Once again, to become negatively charged, you probably had to gain some electrons, so you have them to give and be a Lewis base. A ligand has to have at least one unshared pair of valence electrons. So again, water's polar, so it's got those oxygens, nitrogen, again, the chloride here, and something like carbon monoxide. Now, when we talk about how many ligands are attached to the metal, we sometimes refer to it as the coordination number. And the coordination number is how many atoms from the ligand are directly attached to the metal. So however many ligands you got, how many atoms are directly bound to the metal. So in the case of water, it's going to be the oxygen that's going to bind to the metal. In the case of the nitrogen, it is going, or the ammonia is going to be the nitrogen that's going to bind in there. Not all ligands are the same in terms of how they bind. There are some, as we see on the bottom there, which is what is referred to as being monodentate. Some books call it unidentate. And that basically means that for every molecule or atom that's there, basically only one atom binds in. So in the case of water, it's just the oxygen that's binding to the metal. In the case of ammonia, it's just the nitrogen that is binding to the metal. But there are some ligands that are what are referred to as being bidentate. Ethylenediamine, which is abbreviated with an EN. By the way, it's EN is used in the formula. It's also used in the name. It looks something like this, a little NH2 action, some CH2, CH2, NH2. And it's both of those nitrogens within this ethylenediamine that can bind to the metal. So in the case of EN, you actually get like a 2-for-1 deal on that. For every one of those guys, you get 2 atoms that are binding in. And that affects the coordination number, because if I had something like this, I want to know the coordination number here, what would it be? This is my ligand. There are 3 of them. Each of them bind in 2 places. The coordination number here will actually be 6, not 3. So it depends on the ligand, as opposed to if you had COF6, 3 minus. This ligand is monodentate, which means the coordination number here would also be 6 as well. So it's not always going to be the number that you see next to the ligand. It can be if they're monodentate, but if they're bidentate, you do need to adjust for that. Another very common bidentate is our friend oxalate. So oxalate, C2O4 2 minus, looks something like this. And for every molecule of oxalate, this oxygen will bind and this oxygen will bind. So once again, you get a 2-for-1 situation that's occurring there, and it will be able to bind in that case. There are some that can bind in lots of places, like EDTA, that's ethylenediamine tetraacetic acid. That is a mouthful. But it could hit like in 6 places per 1 molecule. So that's something that's really good at like grabbing onto a metal. It will wrap around it in 6 different locations on one of those molecules and basically tie it up. Any questions on that there? So how do you know how many sort of ligands and coordination number you'll get? There are certain patterns that develop. Typically things with a lower positive charge like +1, or typically make 2 in terms of the coordination number, occasionally 4. Guys with like a +2 can go 4 and 6, and guys with +3 typically will kind of coordinate out with 6 very commonly. Gold, though, will usually hang out with 4 in terms of its coordination number. How many come in there? Here's a prettier picture, I guess, of that. And here is our EDTA, which once again can bind at the oxygen here, the oxygen there, the nitrogen there, the nitrogen there, oxygen and oxygen. So at 6 different locations within this one molecule, it basically can tie up that metal in this particular case. By the way, it probably has got like a -4 charge in case you're curious about EDTA. Each of those oxygens are probably -1 charged. Here's a table. You have a similar table in your book of some common unidentate, monodentate, and bidentate. So all of our halogens, thiocyanate, nitrite, ammonia, cyanide. Here's our 2 that are the ones we talked about, EN and oxalate. This is diene here, which actually could go in 3 places, each nitrogen able to bond in there. And once again, there is our EDTA on the bottom. And like I said before, -1, -1, -1, -1. So probably looking at like a -4 charge overall on that. All right, so why don't we take a look here? What are the oxidation numbers on the metals in the complex ion? By the way, most of the time when a coordination compound is written, the guy in the box is the complex ion part. All right, so take a second, figure out the oxidation state on the complex ion metal and see what you come up with. First off, the part here would be our complex ion, which, by the way, in this case would mean the potassium here is our counter ion. In terms of charge, our oxidation state on the gold, which is what we're looking at here, OH is OH minus, which is -1. There are 4 of them, which gives you a -4 overall. Potassium is +1, so to balance it out to 0 here, the gold should be +3 in this case. That means if I pull out just the complex ion part, the charge on the complex ion would be overall -1, yeah? And again, -4 for the OH, +3. That is why our counter ion, we have just 1 potassium, just like an ionic compound to balance those guys out. +1, -1 gives us 0 in this particular case. Question on that there. Coming over here, once again, this is our complex ion. Over here, our nitrate here would be our counter ion. So NH3 has no charge. Nitrate is -1, and there's 3 of them, which gives us a -3. So to balance out here, the chromium would also be carrying a +3 charge, our oxidation state. That means if we pull out just the complex ion part of this guy, it has an overall charge of +3, which is why in this particular case, we need not just 1 nitrate as our counter ion, but we need a grand total of 3 of them to give us a -3 to balance it out. So that is what's going on here. Also, nice demonstration. One case the complex ion is negative, one case complex ion here is positive. So the oxidation state of both of those metals there is +3. Any questions on that there? Okay. Then let's talk about everybody's favorite thing, which is naming. I know you thought all your naming stuff was over. One more naming here for the road. The cation is always named before the anion. So as we mentioned before, pretty much works like a normal ionic compound. Again, positive, then negative, both in formula and name. Within a complex ion, you name the ligands in alphabetical order, regardless of prefix. So for example, if you had, say, 2 Cls in it, it would be dichloral. You would look at just the C, not the D for the di. So you ignore the prefix if there happens to be one. The names of some ligands will end with O. Some neutral ones are usually called by the name of the molecule, but there are some exceptions. Water is called aquo. Some people also call it aqua. Okay. CO is carbonyl. NH3 is amine. As I mentioned a second ago, if you happen to have multiples of the same ligand in a compound or a complex ion, you can use prefix like di for 2, tri for 3, tetra for 4, penta for 5, hexa for 6. Now, if the ligand actually already in its own name has a prefix, then you roll to bis, which is 2, tris, which is 3, tetrakis, which is 4. For example, our EN guy, which is ethyl endyl diamine, because it already has the di in it. If you had 2 of them, you would use bis instead of di for the prefix. So that is what that is referring to. The oxidation state of the metal is normally written at the end of the complex ion name. And We do use Roman numerals to indicate the charge on the transition metal, or the metal in the complex ion. And we even use Roman numerals for things that we normally do not in other situations. So for example, zinc and silver, which have a fixed charge, we normally do not use Roman numerals, but in this type of naming, you still use the Roman numerals for those guys as well. In addition, as odd as it may sound, you could end up with a metal that has no charge. So you put a 0 there in the parentheses instead of a Roman numeral for that as well. Now, the metal part of the name should always come at the end of the complex ion name, not necessarily the end of the coordination compound, but at the end of the complex ion part of the name is where it should come with the Roman numerals. Lastly, if this was not all fun enough, if we are rolling with a negative complex ion, then we actually will roll with the old school name for everybody that ends in 8. So instead of iron, it'll be ferrate. Instead of copper, it'll be cuprate. Instead of lead, it'll be plumate. So we kind of go with those sort of older naming that ends in 8 for those guys. Question on those things there. So let's take a look at a couple more things here, and then we'll go back to that, I think. So here's a table similar to the one you have in your book there. Some neutral guys in their names. So aqua amine, methylamine. Our halogens are named like you do in organic: fluoro, chloro, bromo, iodo, hydroxo, and cyano there for cyanide. And here's what I was talking about. If your complex ion is negatively charged, you would roll with ferrate, cuprate, plumate, argentate, arurate, and stannate for those guys. And again, here's a couple of other sort of names that sometimes come across. Again, bromo, chloro, hydroxo. We got some carbonate. You could order a carbonato, and then maybe you want an oxalato, like I'm at Starbucks, and you could get it with like carbonel or an aquo and stuff like that. That is ethyl endyl diamine, and that's EDTA down here as well. So if we go back to take a look at the, what are those guys there? What do we have there? AuOH4. So we had this guy here. Right. And so if we were to name this, we would start with our counter ion in this case. All counter ions are pretty much just named with the name, regardless of how many you have of them. So if you have like K2, K3, it doesn't really matter. So this would be just potassium, which is our counter ion name. We would then look at our ligands here, and that is hydroxo, which should be here. We also have 4 of them, and the prefix for 4 is tetra. So this would be tetrahydroxo. All right. Now, we already established that this guy here is a negative complex ion, and I know that because it comes second in the formula. So what we're going to roll with here is the old school name for gold, which in this case would be arurate. I'm running out of room, so I'm going to go underneath it. Arurate, Roman numeral 3. So this guy would be potassium tetrahydroxo. Arurate 3 would be the coordination compound. First off, any question on that name there? If I had just a complex ion by itself without the counter ion there, the name would be just the last part, tetrahydroxo arurate 3, and then you simply just put ion at the end of it because it's an ion. So that's typically how you go about naming just a complex ion by itself without obviously the counter ion that is present. Question on that one there? Yeah. We did it in that previous example. So you would go through, like we did before. This is hydroxide, which is -1, right? And that gave us the -4. This is potassium with a +1 charge. Again, to get us to 0, the gold here would be +3. which is where the Roman numerals obviously here come from. Yeah. Other questions? So while we're at, why don't we go back to and take a peek at the other one that was there? So that is that one right there. So why don't you give this one a go? Why don't you name this guy here and see what you come up with? Okay, let's take a look. So first off, in this case, we already determined earlier that our complex ion is positive. We also determined that the chromium has a +3 charge earlier. That also means we could just use the regular name there for the metal in this case because it's a positive complex ion. Our ligands here are ammonia, and there's 6 of them, which would be hexaamine. Then it would be chromium, Roman numeral 3. So once again, this is the complex ion part of the name, and the metal should always come at the end of it with the Roman numeral. And now we're left with our counter ion, which is nitrate. And even though, again, there are 3 of them, it does not make a difference. This would then be nitrate. So hexaamine, chromium 3 nitrate. Obviously, if we had just the complex ion by itself, it would be hexaamine, chromium, Roman numeral 3 ion, which would be the name for this guy by itself. Question on that name there. By the way, coordination number for the first guy would be 4. Yes, those are all monodentate, and coordination number for this guy would be 6. Yeah, again, each of the NH3s are monodentate, so there'd be 6. Question on any of that there. All right, so let's try some here more, I think. We'll skip that one. Let's just go to these 2, I think. Do you have a question? You're good. Cobaltate. So once again here, just from the positioning, we can see that our complex ion here is going to be positive, followed by our counter ion, which is going to be negative. Looking at our oxidation state on the chromium, water is zilch, chloride is -1, there's 2. There was also a chloride on the outside there in our counter ion, so that's a -3 overall. So in this case, our chromium is taking a +3 oxidation state. Yeah. We can roll with our ligands. So we have 2 chlorines, so that's going to be a dichloral situation. We also have 4 waters, which would be a tetra aqua or aqua, your choice. And we do want to put it in alphabetical order. Which one should come first? Yeah, it should come this one because we're actually comparing the A to the C here. Again, we're going to ignore the prefix there. So this would be tetra aqua dichloral. We can now use the whole name of the metal there, which would be chromium, Roman numeral 3. And now for our counter ion, just named like normal, IDE at the end of that guy would be chloride here. So tetra aqua or aqua, dichloral chromium 3 chloride. Any question on that name there? All right, we have the name. We want to put it into formula. So really, we just want to take the pieces. This is ethyl endyl diamine, and most people, once again, do just use EN for it. And you can use it in the formula, you can use it in the name as well. We do use tris here, which means 3, and that once again is because this already has a prefix in its name. That means we got 3 of those guys. We also have a cobalt that has a +2, I think it says here, +2 charge there. So if we put these guys together, our CO and our EN3, what would be the overall charge on this? It'd be +2 in this case, as En is neutral, and that has a +2 charge. So the complex ion part is +2. The reason that's important is because this is our counter ion, right, which is sulfate, which means in this case we actually only need 1 of the sulfates to balance it out. Because if we do this guy, that -2 and +2 will cancel out. We won't have any charge though, so we do put it together like so. SO4. question on that one there? So really with the name, you just want to kind of put it together, the pieces correctly, figure out the overall charge rate, complex ion, and then use the appropriate number of counter-ions. Questions? Okay, let's try a couple more here. Fun with naming. There we go. All right, so for both of these, let's do the name. Okay, so once again, look at this complex ion part there, counter ion there. So once again, it's positive. Ammonia is 0. Chloride is -1 and -1 on the outside. And there's 2 of them. Give us a -2. So that does give us a cobalt that is +3. By the way, it just happens they're all +3s here. They're not always going to be +3. It just so happens. That is what we're looking at here. We are going to go with penta for 5, amine for the ammonia, chloral for the chlorine that's inside the complex ion. And obviously we can roll with the whole name there of cobalt with a Roman numeral 3 and a chloride at the end there. Coordination number on this guy would be 6, yes, 5 ammonias and 1 chloride. So the coordination number would be 6 in this case. Question on that name there. Yes. Yeah, you usually won't use mono. So you, and anything where there's 1 in terms of a ligand, you just kind of just use the name of it and stuff like that. Yeah. Other questions? Secondly, here we see actually our counter ions first. Our complex ion is second. Once again, CN is -1, which is cyanide. There are 6 of them, gives us a -6. We do have a +1 on the outside, and there's 3 of them. So to balance everything out, once again here, the iron is 3. We will start with the counter ion, which will come first because it is positive in this case. So that it will be just, again, potassium. It doesn't matter that there's 3 of them. So just like when you name K2O, you call it potassium oxide. So the same idea here. We will go with hexa, cyano, and a little ferrate in this case, because the complex ion is negative. We're going to use the ATE version of the name, not forgetting to put our Roman numeral of 3 in this case. Any question on any of those names there? Once again, obviously, if you took out the counter ion on either of them, you just take out the counter ion part of the name and put ion at the end of each of them, and you would have the name for the complex ion part. Coordination number on the bottom guy there would also be 6 as well. Any question on any of those 2? All right, 2 more here. Let's do a little bit of formulas for each of these. A little triamine, bromo, platinum 2 chloride, and potassium hexafluorocobaltate 3. So once again, I'm just going to kind of pull out the parts. So tri means 3, amine means NH3. So I definitely got an NH3 in 3 of them. That takes care of that part. I got a bromo, which is a Br, takes care of that part. And I got a platinum that has a +2 charge. So kind of putting all that together, kind of put these guys in like so. Once again, here is probably helpful to try to figure out what the overall charge is so you can figure out your counter ion, what you need. So obviously that's +2, that's a zilch, and that is a -1, which means overall here we are rolling with a +1 charge on the complex ion. That means that our counter ion, which is chloride, we actually would just need 1 of them to balance it out, which would give us something that looks like this. Any questions on that there? Same thing here. We see potassium, which is our counter ion. This is our complex ion. By the way, I know that because the metal always comes at the end of the complex ion name. So that is definitely that metal part. So once again, potassium is K+. We have hexafluoral, which is like 6 fluorines. And we have a cobalt that has a +3 charge. So once again, just kind of building the complex ion part. That's obviously going to give us a -1, -6, and a +3. which means overall we are going with a -3 on our complex ion. That means we're going to need a few of these guys, right, to balance it out. So we will end up with 3 of them and something that looks like that. Any questions on that there? Any questions on naming or writing formulas, oxidation states, coordination numbers for complex ions, coordination compounds? By the way, the coordination number on this guy would be, it would be 4 in this case. So there's something different. There we go. Coordination number on that guy would be 6 in that case. Yeah. Any questions on that? Okay, I'm just going to run a little bit over and then we'll take a break and we'll go check out a lab. But I just want to kind of maybe hit one more topic here. So about 10 more minutes and then we will wrap it up here. Forewarning, I am going over time. All right. So that way we don't have to stop and restart. Sort of, we just want to talk a little bit about isomers and sort of complex ions and so forth. Isomers are guys that have really the same formula, but some different connectivity. And there's several different types of isomers we're going to kind of go over here in just a second. There are structural isomers, which have different bonds. So a type of structural isomer is a coordination isomer and a linkage isomer. We'll look at each of those in just a second. There's also stereoisomers, which have the same bonds, but sort of different arrangement in three-dimensional space. And that gives rise to geometric isomers, which are cis or trans, are optical isomers, which have the ability to sort of move plane polarized light. So let's take a look at some of these isomers and sort of some of the differences here. These are coordination isomers. And the main difference here is they have exactly the same guys. 1 chromium, 5 NH3 is a sulfate and a bromine. But in the first case, part of the complex ion is the sulfate, is actually attached directly to the metal in the complex ion. And it is the bromine here, which is the counter ion in the first guy. Now, different to that, including this guy should be over there. There we go. This is our complex ion here. And the difference is we still have the 5 ammonias, but in this case, we actually have directly attached to it is the bromine. And again, here serving as the counter ion in this case would be the sulfate. So these are what are known as coordination isomers. And the main difference here is obviously we have a different sort of ligand attached to the metal, while the other one is obviously serving as the counter ion in that case. Any questions on that type of isomer? Draw them all in. I think I'm missing one. Put one there. Okay, so that's a coordination isomer. The next type of isomer is what is referred to as a linkage isomer. And in this situation, what you have is you have a ligand that's attached to the metal in the middle of the complex ion. But because that ligand actually has the ability to attach in different locations. So we're not talking like a bidentate where there are 2 locations attaching. But in the case of NO2 here minus, it has the ability to attach to the metal through the nitrogen because it's got the lone pairs on it. But that same ligand can decide I would like to attach through the oxygen, which also has some lone pairs on it and is making that attachment. So again, they're each sort of attaching monodentate one time in, but it is actually a different atom on the ligand that is attaching. And that's what is referred to as a linkage isomer. It's actually, like the name implies, the actual part that's linked to the metal is different on the ligand in each of these cases. Obviously, everything else in this sort of guy is not listed there. They would all be the same. And again, the sole difference in this type of isomers, these 2 guys, is that actual linkage between the ligand and the central metal. Any questions on that there? Now, stereoisomers give rise to what are referred to as cis or trans isomers. And in general, cis means the same side, and trans means opposite sides. You usually come across a lot of that in organic chemistry, I think I remember before I failed. But we usually talk about it in a double bond situation. So for example, those two groups are on the same side, that would be cis. And those two groups are on, say, opposite sides, that would be trans. In the case of sort of complex ions, what we're usually talking about is kind of the same side of the plane or opposite sides of the plane. So there's sort of a plane of the complex molecule, and those guys are either sort of on the same side of it or opposite sides. If it's sort of square planar, maybe they're both on the same side. If it's more of an octahedral sort of deal, maybe you have one above the plane and below the plane of the molecule, and that would obviously be trans. So we're talking more about sort of spatial arrangements for cis and trans. So this is a square planar. If you remember square planar geometry, right? Has a square within the plane, right? It's octahedral really is, you got the other guys there, the non-bonding electrons. But in this case, the NH3s are on the same side, so that would be cis. You can even look at the chlorines if you like. They are also on the same side of the plane. As opposed to over here, the chlorines are on opposite sides, which would be trans. And you could also look at the ammonia here on opposite sides, which are trans. So in order for cis or trans, you got to have at least two groups that are the same that you're looking at and sort of comparing. So you got to have two guys that are basically the same to compare and sort of their location. As you can see, it gives slightly different sort of characteristics. One's yellow, one's more pale yellow, and they'll sometimes put trans or cis in front of the name or the formula to indicate which one they are talking about. So that square planar, that obviously would be a coordination number of 4 happening here. Yes, so coordination number 4 is what we're looking at here. This is more of an octahedral arrangement with a coordination number of 6 happening here. And in this case, we have our trans and our cis. So you can kind of think of this as like the plane of the molecule, and we have a chlorine above and kind of below the plane of the molecule. And that obviously is on opposite sides. So that would be trans, as opposed to here where sort of the chlorine and the chlorine are now sort of on the same side. Maybe a little bit easier to see on that guy there of the molecule there. And it would be cis. Again, they both have identical formulas. The only difference is the location of those guys. Now, cis and trans isomers can basically, or optical isomers can have an opposite effect on plane polarized light. And we can create what are sometimes referred to as chiral molecules. Chiral molecules are molecules where if you back it up to the mirror, and you take the mirror image out, it is non-superimposable. So that is like if you put your hand up to the mirror, you get your other hand, faces you, yes. You take your other hand out of the mirror, you can do as much as you like with that hand, rotate it as much as you like and try not to break your hand. But you can never get them to sit correctly, even though my thumbs are correct, one's palm up, one's palm down, right? I could go this way, which my thumbs are on the wrong side. So you'll never be able to really rotate a chiral molecule's mirror image in a way where it will perfectly sit on top of the original sort of image, if you will. That is what a chiral molecule is. Something that's known as achiral is a molecule where if you take the mirror image out, you can, with sufficient rotation, get it to fit like perfectly kind of on top of the original guy. And obviously plane polarized light, if you wanted to, and we're not going to do that, you can measure the angle of rotation and stuff like that. That's not important for us. There's our hands. There we go. So let's take a look at some of these, and there are slight differences of sort of what is different on some of these, and I'll just try to point those out to you. So isomer 1 and isomer 2 are mirror images that cannot be superimposed, so they are chiral. So this is our original isomer. When we stick it up into the mirror, everybody gets reflected, right? And what happens in the reflection is the original connectivity is this nitrogen to this nitrogen. But when that gets reflected in the mirror image, there's actually a change in sort of what gets connected. Now those nitrogen goes to the back, and we have this longer connection happening here, which means when we pull that mirror image out, we're going to rotate, but there's always going to be something that is not going to line up right because we've kind of changed the connection in the mirror image of it, kind of like our thumb. Our thumb's always going to be on the wrong side, or we could get our thumb to the right side, but then we're palm up and palm down. So as you rotate, you will not be able to do that in this mirror image of each other. And here's a better look at it, perhaps. Number one, here's our trans. And again, our trans is our chlorine up on top and up on the bottom. So when it gets reflected, gets reflected, gets reflected. This guy gets reflected back. What we actually see here is we actually maintain the same connectivity in the mirror image. So you actually can pull out that first guy's mirror image and you could rotate it and it will fit perfectly on top of the original guy, because we kind of maintain really the same connections in the mirror image as what we had. And that usually occurs when you got, you know, the same groups kind of hanging out on the same side in the trans sort of situation. Now in our cis situation, once again, it is this little difference here. The nitrogens are connected up front for us. When they get mirror imaged in the back, and now connected to the back, which means when you pull out that mirror image, these guys are not going to always be in the right location. Something's going to be in the wrong location when you kind of rotate it around, and you will not be able to superimpose that on each other. And that sometimes happens a lot with cis isomers in these cases, because they get that reflection that occurs. You get that sort of weird, wrong connectivity that occurs in the mirror image, which when you pull it out, you cannot get it to superimpose. So two molecules that have mirror images that of each other that are non-superimposable are sometimes also called enantiomers. A lot of biomolecules are chiral. Some drugs are also chiral, but only one isomer may be effective in curing a disease. So in terms of isomers and the cis and trans, you know, sometimes it's really hard to kind of visualize those things, but it is sort of when you kind of reflect things in, you will get some different connectivities that will occur a lot of times in the cis guy, and it will create a chiral molecule that really will not be superimposable. A lot of times in the trans, you got kind of same groups kind of in the same locations. So when they do sort of mirror image each other, they kind of will kind of fit okay, the mirror image on top of each other. Question on isomers. As promised, I'm done. All right. Any questions?